Hello, yes, the camera angle is a bit different, but sometimes it's good to take a fresh perspective on things. This video is about the Shunting Yard Algorithm, which is one of several techniques to turn a handwritten expression, mathematical expression, into something a computer can solve. This is the first step anybody would need to take on the road to creating their own programming language. The Shunting Yard algorithm is one of those classical computer science algorithms, so if I am about to solve your homework for you, then you can thank me later. One of the first problems with parsing anything is to understand that humans are inherently flawed. Take, for example, the following expression. 1 plus 2 times 4, take 3. Solving this for the average social media user is obviously quite befuddling, but for the rest of us that went to school, we understand there are a set of rules we must follow. We would normally do multiplies first. In this case, it would give us an 8. 1 plus 8, take 3. I say take because I'm from the UK, but I do mean subtract to all of those that aren't. We then also understand that addition and subtraction are pretty much the same thing, so it doesn't really matter what order we do it in, so we can solve this as being 9, take 3, and then that of course equals 6. We were able to get to the correct solution because we understand that there are an order of operations. Now, for the purposes of today's video, I want to be very clear on what I mean by the terms operators. So operators are the things that occur in between values. And all of the operators today, I'm going to assume, take two arguments. They're the values either side of them. Some of those operators were more significant than others. They have a higher precedence. It's important that we compute those first. And I learnt the order as being brackets, operations, division, multiplication, addition, and subtraction. BODMAS. That's a particularly strange UK thing. I think the rest of the world learns parenthesis, exponents, division, multiplication, addition, and subtraction. PEDMAS. So in this case, it really does depend on where you're from. Now, despite these operations having groups that are fairly similar, so division and multiplication could be considered similar, addition and subtraction, as we've just argued, are quite similar, we can actually label them with a precedent. So I'm going to say subtraction is the least important and will increase in priority. This implies that if we see any divisions, we must do them before we do any additions. The first problem we're going to try and solve when solving an expression like this is computers don't see what humans see. A human will read this from left to right, certainly in English, and because we are trained to, we will put in virtual parenthesis or brackets in order to emphasize the priority and order of the computations required to solve this expression. It turns out there's a really elegant algorithm for doing this, and it's called the Shunting Yard Algorithm. And rather than describe it first and then show it, I'm going to show it visually. So one moment please whilst I set up my visual computer. Right, this is my visual computer. It looks very much like my kitchen worktop. And on the left here, I've labelled some rows, which we're going to use to help sort this computation. I'll describe what these are as we go along, but let's start by entering our expression into our computer. So we've got 1 plus 2 multiply 4 subtract 3. Note that on the operators I've put the number that represents their precedence. Now I'll establish some simple rules in order to sort this into a different form of notation called reverse Polish notation, RPN. And this is a different way of representing an expression without the ambiguity that we can see in this more traditional way. So rule number 1, starting from left to right as we read in each token of the expression. Now in my setup, each token is going to be one character and every operator assumes there's a character either side. We're not doing any sort of error catching or anything with my visual computer. So rule number 1 is we read from left to right, and if it's a digit, a character, a numeric literal, we push that straight to our output. Now output could be a stack, it could be a list, anything that's traversable. The next token is the addition operator. Operators by default go onto the holding stack, providing they are a higher precedent than what's already at the top of the stack. My stack was empty, so it's okay. Let's read in our next token. It's the literal 2. That goes straight to our output. Now let's read in the next token, multiply. We're going to push that onto our holding stack. We can do this quite happily because we can see that the precedent of our multiply is 3. The top of the stack, it was 2, so that's fine. Let's take our next token. We push that to our output because it's just a numeric literal. Then we take our next token, it's an operator, and we try to push this onto our holding stack, but we can't because the precedent of the subtract operation is lower than the precedent of the top of the stack. So at this point, we need to now pop things off the stack. I call it flushing them out of the stack. So we're going to flush this out of the stack and into our output. Let's try again, pushing the subtract operator on. Again, we still can't do it because the precedent of the subtract operator is lower than the precedent of the top of the stack, which is addition. So we'll drain that one out, flush it out. And now there's nothing in the stack, so of course we can push that operator into it. Next token. Well, this time it's a numeric literal, that just goes straight into our output. And you'll see we've nothing left now on our input expression, but we have got something left in the stack, so we're going to drain the stack out. Now I appreciate this looks like just a jumbled up version of our input. It's actually the reverse Polish notation form of our input expression. And it's got some useful properties, particularly regarding computation. Now, recall all of our operators take 2 arguments, one either side. You can't treat this as an expression like we did before. It now needs to be computed, and to compute it we solve with another stack. Starting from left to right, let's push the values onto our solving stack. Well, I'm just going to push the value 1, and I'll push the value 2, and I'll push the value 4. Now, this is our first operator. I'm going to push that onto our solving stack. We know that it's an operator, and we know that all operators take 2 arguments, and in fact it takes the 2 preceding arguments on our stack. So let's just rearrange those. 2 times 4, that's something we can obviously solve. That becomes 8. Move those out the way, and we can push the solution onto our solution stack. Let's take the next token. It is our addition operator. Well, same thing applies. We've got the 2 preceding arguments. They become the 2 arguments of that operator. Let's rearrange them. 1 plus 8, well, that is something we can solve. Let's take the next token. Well, we can't do anything with that. It's just put it on the solution stack. And take our final token and push that onto the solution stack. It's an operator. It takes 2 arguments. They happen to be the 2 preceding arguments on the solution stack. So let's rearrange it. And let's finally solve that. And we can see we've got nothing left in our RPN. We've got 1 value left at the top of our solution stack, and it happens to be the correct answer for the original expression. So that's how the Shunting Yard algorithm works. It's time to code it up, but we're going to make lots of assumptions to simplify the problem so we can keep this video quite concise. I'm going to whiz through the code pretty quickly today, and I've started with a blank int main C++ program. Well, it's almost blank. I've included some of the standard library which I think I'm going to need. If you're not familiar with an unordered map and a double-ended queue, I've actually made a video about C++ containers before. You may notice the omission of stack. I don't like the standard library stack implementation. It's a bit too rigid for my purposes. It's very much the textbook stack, which means we can only access things at the top of it. Given that we want to fiddle about within the proximity of the top of the stack, a double-ended queue is better, and we'll make it behave like a stack by rigidly enforcing pushing to the front and popping from the front only. Also, using a double-ended queue means we can effectively iterate through our stack, which is useful for visualization and debugging purposes. I'll start today by defining an operator struct. This is a place to store the precedence of the operator and the number of arguments it operates with. Even though in the demonstration this was always 2, we'll see before the end of today that sometimes we want this to be 1. Operators are a special case token in our input expression. They signify a computation needs to occur. I'm going to use an unordered map of my operator type, indexed by the char type, to assign precedence and the number of arguments to a given character in our expression. Here we see the precedence increases as we apply the rules of BODMAS. Next, we're going to need the expression itself, which I'm storing as a standard string. I'm making some bold assumptions about error in this case. Firstly, I'm assuming that there will not be any. And secondly, I'm assuming that the input expression doesn't contain white space or invalid characters. This is just to keep this particular implementation clear, and of course we will have to look at error in the future. The demonstration showed that we needed 2 containers to implement this algorithm. We needed something temporary, I called it stack holding, that holds things, and we needed some sort of output that also held things. I'm going to call those things symbols. Without getting too bogged down into compiler parlance, I'm going to assume that a token makes up a particular thing within the expression. It could be an operator, it could be a literal. And a symbol is a token that has meaning attached to it. For convenience, I'm going to store a string version of the symbol. And I'll add to the symbol struct an enum class with 3 entries, one for unknown, one for literal numeric, and one for operator. That's all we have right now, and default it to unknown. Those of you reading ahead may think, well, why are we not using a C++ char or character? Well, because symbols may in the future consist of more than 1 digit, but for today they do not. If our symbol happens to be an operator, I'm going to store the properties of that operator. Now I've defined what the thing is our containers can contain, I can create those containers. So here is my holding stack implemented as a double-ended queue of type symbol. And here is my output stack of the same. Now let's implement enough of the Shunting Yard algorithm to replicate the functionality seen in the demonstration. I know I need to iterate through each character of my input expression. For clarity, I'm going to make some very bold assumptions again. Firstly, all of my numeric literals are going to be single-digit numbers between 0 and 9, so 10 would be an invalid entry. Secondly, all of my operators are a single symbol. Naturally, that's a bit rubbish, but we'll see how to expand upon that in subsequent videos to this. If the input character is a numeric literal, we just want to push it straight to our output container. So I use the isDigit function of the standard library to determine this, and then I construct in place a symbol struct identifying that our symbol is a literal numeric. If it's not a digit, then perhaps it's an operator. Since I have stored my operators in an unordered map, I can use the contains function to see if the input character is used as a key for any of the entries in that map. I think you need C++20 enabled to see this function. If the map does contain the operator, I'm just going to grab it as a convenient variable called newOp. This is where the magic begins. We know that we can't add the operator to the stack without checking the precedence of the operator at the top of the stack already. If the operator at the top of the stack has higher precedence, then we must remove it from the stack and add it to the output. And we'll want to keep doing this until either the operator at the top of the stack is lower precedence or the stack is empty. I'll create a little while loop to make sure that we can't operate on an empty stack. And I'm going to check that the operator at the top of the stack is indeed an operator. As I mentioned before, we may expand upon this algorithm to be a little bit more sophisticated. If it is an operator, I'm just going to create a convenience variable to access it. Now I can do the precedence check. If the operator at the top of the stack has higher than or equal precedence to the operator we're trying to push onto the stack, then push onto our output the top of the stack, and then pop the top of the holding stack. For now, this loop will keep running until we've popped everything off the stack, or it'll stall, so we need a breakout clause. Well, that's quite trivial, because we want to stop when this condition is not true. We've now finished doing the precedence checks with the stack, so we can push the new operator to the top of the holding stack. And just like I did with the numeric literal, I'm constructing it in place, classifying it as an operator, and copying in the properties of that particular operator. If what we read in is not a digit, and it's not in our map of operators, then it has to be an error. I'll display an error message and exit the program. This loop represents the first phase of our algorithm. There may, however, still be things remaining in the holding stack. We now need to drain that holding stack into the output. This too is pretty trivial. Whilst the holding stack has things in it, pop them out of the holding stack and push them into the output. I think at this stage it would be useful to see if this is working. So I'll display to the console the input expression. I'll now display the reverse Polish notation version simply by iterating through our output container and displaying the symbol. Let's take a look. Reassuringly, we can see that this matches the demonstration earlier. Let's test it by adding a few more things. Do you know what? I'm going to assume that's correct. Let's put that back. Up to now, we've implemented the parser and the tokenizer, and we've arranged things in terms of operator precedence. Now it's time to implement the solver, the thing that will actually compute the expression and give us a result. Once we've reached the reverse Polish notation stage, we now need to think about solving it. As you've already seen with some of the code so far, there are the footings, the placeholders of something a little bit larger in the future. The same philosophy will be applied to our solver. I know that I'm going to need a stack that stores the values which are the results of the various computations. In this case, again, I'm going to use a double-ended queue of type double. This does imply that all of our mathematics is going to operate on double precision values. And of course, that may yield all sorts of accuracy problems in its own right. But for now, keep it simple, then make it work well. My output stack isn't really a stack, but it's a sequence of the reverse Polish notation. So let's iterate through that. And this is one of the reasons why you can't actually use a standard stack, because you can't iterate through a stack. The things in this output container are my classified symbols. This means I can be proactive about deciding what to do with them. I classified them as either operators or numeric literals. If the symbol happens to be a numeric literal, then I'm just going to push its numeric value to my solution stack. I'm using the standard string to double function to convert the string in the expression into a numeric literal to push onto the stack. If my symbol happens to be an operator, then we know we must perform some computation. For now, we know that all of the operators take 2 arguments. Those 2 arguments happen to be the 2 things at the top of the stack. However, in the future, our operators and other things may have variable numbers of arguments. But for now, I'll create a standard vector of type double, the size of the number of arguments that operator required. I'm going to pop off the solution stack, the number of values required by that operator, and place them into this vector. I take the top of the stack each time, which conveniently with a double-ended queue is always in index 0. But I do need to be a little bit careful here. If the reverse Polish notation happens to be invalid, then our solution stack might not have aligned with the requirements of the number of arguments of that particular operator. So I'm going to put a check in to make sure that the solution stack isn't empty each time we try to read from it. If it is empty and we're still expecting to read from it, then the expression was bad. That's an error. And we will have to inform the user that an error has occurred. Once we have filled our temporary memory vector with the values necessary to perform the computation, we actually need to do the computation. So I'll create a variable called result, and I will check that the current operator does indeed have 2 arguments, and I will just implement the arithmetic for those operators. Once I've computed that result, I can push it onto my solution stack. The implementation of the solver, again, is not very long or complicated. Hopefully, if it's all worked, we'll be left with 1 value on our solution stack, and we can display that 1 value, it'll be at the top, as the end result. Let's take a look. Satisfyingly, we see that this is exactly the same as the demonstration. Even though we limited our input tokens to be single digits, the computations don't have to be. Let's try this one. Very nice. What we have built here is a very simple calculator that obeys the order of operations of basic arithmetic. It is lacking quite a few features. The first of which is we've not handled parenthesis or brackets of any sort. Being able to manually specify the order of operations is an incredibly important part of all mathematics. So let's consider how we handle this scenario. This time my expression is a little bit more complex. I've added parentheses or brackets, which as we know changes the order in which we need to compute things. According to BODMAS, we would compute what's in the bracket first. Well, we can apply exactly the same algorithm and get the same result. We just need to introduce a new rule, and that is what do we do when we encounter parentheses as part of our input. So let's run through the algorithm again. It's a numeric literal, a value. We can just push that straight to our output. We read in our next token, it is an operator, we'll push that onto the holding stack. Next token is a literal, push straight to the output. Next token, multiply, it's got a higher precedent than what's already on the top of the stack, so we can push it to the top of the stack. We've now got our open brackets, parenthesis. It's not an operator, and I'm just going to push it onto the holding stack regardless of any precedence, because I'm going to use it as an indicator of when to stop draining the holding stack later. Let's continue. Read in the next token, it's a value 4, and push that straight to our output. The next token is a subtract. Now it's got a low precedent, but the item in the stack doesn't have any precedence indicator at all. We could assume it's 0, even though oddly we said in BODMAS brackets had the highest precedent. How we actually implement that in code, we'll see later. But for now, we'll just assume that this is a precedent of 0, and therefore I can push the subtract quite happily to our holding stack. Let's read in our next token, it's the value 3. Well, that just goes straight to our output. And finally, we read in our close parenthesis, and this is where we trigger our new rule. Close parenthesis tells us we must drain our holding stack until we reach an open parenthesis. So we can get rid of that, we can take out our subtract onto our output, and we can take out our brackets and get rid of that, and then we just drain the holding stack as before because we've run out of things on our input. We can now go about solving this with our solution stack. Let's push values onto it until we get to an operator, something we can actually compute. In this case, it's our subtract. Well, remember, it has 2 arguments, and they're the 2 things that precede it on the solution stack. So we'll just solve that. 4 take 3, and put the solution in is another 1. Let's read our multiply. Exactly the same, it's got 2 arguments, they're the 2 that precede it. Let's solve it. 2 times 1, well, that just happens to be 2. Nothing changes. And finally, let's push our addition onto it. Again, 2 previous values on the stack, and we can compute the result. It is, of course, 3. That's a little bit more complicated, so let's quickly run through a similar example again. This time, I'll put the parenthesis at the start. Let's work out a value before we start computing this. We know we've got 1 plus 2 in our brackets, must be computed first, so that's 3. Then we've got multiply, so it's 3 times 4, which is 12, and 12, take the 3, is 9. Let's see if our algorithm does it, and we'll try and go through it a bit quicker this time. So our first token is an open parenthesis. We're just going to push that straight onto our holding stack. Next token is the value 1. That can go right through to our output. Next token, addition. Well, it doesn't have higher precedence than a bracket, but it's a special case. So we're going to assume that the precedence of the bracket is 0. Read the next token, it's the value 2. The next token is a closed parenthesis, which means we must flush out our holding stack until we reach an open parenthesis. So we can get rid of u, flush u into the output, and get rid of u. Our next token is the multiply operator. Well, that goes straight onto our holding stack. Our next token is a literal. That can go straight onto the output. And this is why it's interesting, because this is the first time where we've seen operators in the middle of our output reverse Polish notation expression. Read our next token, it's a subtract. We can't push it onto our stack because the operator at the top of the stack has a higher precedent than the one we're trying to push. So we must drain out the stack until we can push it there. And finally, read our last token in, it's a numeric literal, that goes straight to the output. We've nothing left on the input, so we'll drain out the holding stack into our output. Right, let's just quickly run through the solving phase. We'll just push the value onto our solution stack. When we push an operator on, we must compute it. It's always going to be the 2 previous things on the stack. Swap those round and compute it. 1 plus 2 is equal to 3. We'll push those onto our solution stack. Read the next one in, push it onto the stack. Read the next one in, that is an operator. So that means we must push it onto our stack, compute
with the two previous values, and you may even see that we've planned things out a bit here at OLC Studios, because look, 3 times 4 is equal to 12. Look at that, had a card ready and everything. Finally, let's go to our output, push that onto the stack, push the final token onto the stack. It's an operator. We'll try and compute it, and of course 12 take 3 is 9. So we end up with just the value. It's the correct value, taking into account all of the order of operations required in our expression. I thought we'd try one more go just to really hammer home the point. So let's try this expression. 1. If we were to compute this mentally, of course we'd do the brackets first. So 2 plus 4 is equal to 6. And that would give us 1 times 6 divided by 3. Well, the division has a higher precedent, so that becomes 6 divided by 3, which is 2, and then we've got 1 times 2, so the answer should be 2 when we get to the end of this. But let's just quickly now go through the rules. So take our input token by token. Numeric literal straight to output. Multiply goes onto the holding stack. Parenthesis also goes onto the holding stack. Numeric literal goes straight through to output. Addition goes onto the holding stack because it has higher precedent than the bracket. Numeric literal goes straight through to the output. Close parenthesis means drain out the holding stack until we reach a corresponding open parenthesis. Next token is the division operator. It has a higher precedent than what's already at the top of the stack, so we don't need to drain anything. Final token is a numeric literal that just goes out, and now we need to drain the stack. Right, let's solve it. Push to the solution stack, push to the solution stack, and again, now we're pushing our first operator. It uses the previous two items as its arguments, and we can resolve that and push the result back onto the solution stack. Get the next token, push onto the stack, get the next token, it's an operator, so we take the two previous elements, resolve it, and push the solution onto the solution stack. And finally, our last operator, 1 times 2, hopefully we can agree, that is 2. Done.
So let's add the ability to handle parenthesis to our code. We know then that we'll have two additional symbol types, parenthesis open and parenthesis close. When we're parsing the tokens of our expression, we need to look specifically for these two new symbols. So if it is open parenthesis, we don't need to do very much. We don't need to check for precedence. We can just push it immediately onto the holding stack, because the draining out of the holding stack, or the flushing, or indeed the shunting of the shunting yard algorithm happens when we reach a close parenthesis. In this event, we just want to drain the holding stack all the way out until we reach a corresponding open parenthesis. So I'll create a small while loop, which makes sure that the stack is not empty, and as long as the top of the holding stack is not an open parenthesis, drain it out as we did before. Conveniently, we can use this point to check if the holding stack is empty or not. It should contain at least an open parenthesis. If it doesn't, then the parentheses in the expressions were mismatched, and mismatched parenthesis is an error. If the stack then is not empty, it must have an open parenthesis at its top, so we will check explicitly just to double down, pop that open parenthesis and throw it away. We don't care anymore. When we're parsing the operator, we now also want to stop draining out the holding stack if we hit an open parenthesis. To briefly recap, we've added the ability to handle an open parenthesis, which just adds onto the holding stack a token that we can identify. When we hit a close parenthesis, we drain the holding stack until we reach that token we pushed on before. And when we try to push a new operator to the holding stack, during the precedence checking, we can drain the holding stack until we reach that same parenthesis open token. Let's take a look. As with the demonstration, I've put brackets around the 4 subtract 3, and we get the result 3. Let's relocate those brackets. And good, just as in the demonstration, we get 9 this time. Of course, we can be a bit more interesting with brackets because I have more room here than I did on my kitchen worktop. It's nice to see how the reverse Polish notation does start to signify the order of operations. And I'm hoping we should be quite safe against multiple and redundant parentheses. So far, that's all very well and good, but there's one more thing. We're not able to compute negative numbers yet. We need a new operator for that, the unary operator. Negative numbers really are in fact a problem, because many moons ago us squidgy stupid humans decided to use the subtract symbol to also reflect the sign of a number. Is it positive or negative? Now, our briny wetwork can deal with this sort of thing, but our parser can't. The subtraction operator, just like all of the others, was a binary operator. It took two arguments, in this case 4 and 3. If we add in the negation unary operator, it only takes a single argument and applies it to the 3. It takes a positive 3, multiplies it by -1. Fortunately, by examining the history of the expression as we've been parsing it, we can assess whether we do mean a unary negate operator or a binary subtract operator. For example, in this situation, we know that it is a subtraction operator because we've got numeric literals immediately preceding the operator. If we had an operator followed by another operator that was the negate symbol, then we know that this must be the unary operator negate. Likewise, if the preceding expression contained parentheses, we know that this is the subtraction operator. It subtracts 6 from all of this. So we know that if we have a numeric literal or a close parentheses immediately preceding our operator, then it is the binary subtract operator. And we'll put in a special case to detect this. We're going to change our expression to 1 plus 2 multiplied by -4, take 3. If you're curious, the answer is -10. Now, since we're going to be needing information about the previous symbols that we have parsed, I'm going to create a variable symbol previous and literally declare it as the numeric value 0. I'm going to set this value each time we push something to our output. If it was a numeric literal, I'm just going to set the value to whatever we've just pushed out. If it was an open parentheses, well then I know that at the top of my holding stack, I've got the correct symbol for an open parentheses. If it was a close parentheses, I don't have that stored anywhere, so I'll have to manually construct that as required. And for operators, again, I know that I've just pushed something to my holding stack, so that will be the correct symbol that I can store to represent the previous one. My unordered map of operators already contains the characters for plus and minus. In binary terms, they meant add and subtract, but in unary terms, they mean positive and negative. Since they already exist, I'm going to look for them and then change the nature of that operator to turn it into a unary one. For now, I know that I only have a special case for the minus and add symbols. And we determined that it can only be a unary operator if the previous operator was not numeric literal and not a close parenthesis. In that event, I'm going to upgrade my new op variable that we've taken here to have a really high precedence and change the number of arguments so we can identify it as a unary operator. Now, you can see we've got some red squiggles. Well, that's because up here we've got our new operator defined as a const reference to something in this map of operators. And that was quite nice. It stopped us duplicating things unnecessarily. Now, this is an obvious C++ foot cannon moment. If we just remove the const here, the red squiggles go away and you think, oh good, all is good with the world. It's going to work very nicely because we don't need to change any of the code below. It just now gets our modified operator inserted into the holding stack as before. However, what we have also done is very slyly changed the contents of our map of operators. And so every subsequent time we find a minus or plus symbol, we will now upgrade it to a unary operator status. This is fatal to the correct functioning of our Shunting Yard algorithm. Indeed, the solution is to actually provide a genuine copy out of the unordered map. But using the auto syntax does not make that very clear at all. IntelliSense tries to warn you that auto doesn't deduce references, a possible unintended copy is being made, as if it's some really nasty error. I suppose it is not very clear, so let's be very clear and explicit that we are making a copy. A new variable is being created and we are copying the contents from the unordered map. In our solver, we can see that the groundwork was laid before for handling operators with a variable number of arguments. And so alongside our binary implementations, we can have our unary implementations too. Let's take a look. Well, good, the result is pleasingly correct. It is -10. And we can see in the reverse Polish notation that the minus sign here got a higher priority than the multiply sign. And this minus sign, even though we don't visualize it, only has one argument, which is to negate the 4. There is one final little edge case that I want to handle, and that is the case of the very first digit being a unary operator. Let's take a look what happens. Well, it catches it out as a bad expression. And why is this? When we were classifying our operators, we set up a specific clause that it cannot be a unary operator if the preceding symbol was a literal numeric. And we define at the start of our program that the preceding symbol is a literal numeric. It's an odd case, but it is an important one. And I'm going to hack my way out of this one. I'm going to keep a counter to let me know, am I at the start of the expression or not? Now, if I encounter either of these symbols right at the very start of my expression, it must be a unary operator. And this will work providing we remember to increase our pass counter for each character of the expression. Let's take a look. Perfect. Let's just try that with something quite bonkers. Well, I'm going to assume that that's correct too. Who needs testing? And so that's that, the Shunting Yard algorithm. It turns human-readable written mathematical expressions into something a computer can solve, a vital first step when it comes to parsing and tokenizing and implementing our own programming languages, which is something we may look at in the follow-up video to this. If you've enjoyed this video, I've put the source code on the GitHub. Come and have a chat on the Discord server. Give me a big thumbs up, please, because, well, it makes me feel better, and have a think about subscribing. Next time, I'll get the normal camera working, I promise. Until then, take care.